Measures of central tendency, such as the mean, provide an excellent way to summarize the centrality of the data set, so where values tend to centrally lie. But that by itself is not a good description of our data set alone, because we also want to potentially take into account not only the central tendency, but we'd also like to know how spread out our data is. So if I were to tell you, for instance, that in one city the average house price was $250,000, and in another city it was $250K as well, are the two cities equally affordable, assuming they have roughly the same proportion of real estate available? Well, not really. It might be cheaper to go to one city than the other, because if the average is $250K here, but the prices actually range from, say, $100K to, say, $400K, that's going to provide more flexibility than in this other city, in which, say, the prices vary from $200K to $600K. Yet they still have the same averages. So we would like to get an indicator of how spread out that data is. And that's what we're going to do next. That's what we refer to as either the variance or the covariance. Now, we have used some notation in the past, but to keep the notation a little bit cleaner, rather than to write the expected value of the name of the random variable, one commonality is to say the expected value of the random variable x, and then these are the actual instances of that random variable, but we're just going to abbreviate it with the expected value of little x. It'll just make it a little bit easier when we start working with vectors. Okay, so we said that it would be nice to know how spread out our data is, and for this, one measure that's available is what we call the variance. And the variance does the following. Well, first of all, to determine how much our data varies, we usually want to say, well, we need a reference point, right? So we often use the mean as that reference point. So for each value, determine how far above or below the mean it falls. So if we have, let's say, our mean right here, so let's think about this as the mean, and what the mean does is it balances the data, right? So you have these data points, and the idea behind this is that the mean keeps it perfectly balanced. It provides that centrality, and it balances the data point so that the average, we can compute the deviation. So maybe this is what we call x1, and the distance between x1 and its mean is what we call a deviation, right? So here's our expected value of x, and here is one instance of it. So if we compute this distance right here, that distance will be what we call x1 minus the expected value of x. Okay, so that tells us how, in this case, far below x1 is compared to the average. And this will come out to be a negative versus another value, say up here, which let's say we call this x3. x3 will have a positive deviation, x3 minus the expected value of x, because you can see that x3 is above that mean. So that is our next issue that we need to face, is we need to eliminate the signs, because as we'll see, if you add up all these deviations just by themselves, and you're like, hey, look how this is my total spread, well, you're going to get a summation of 0, because that's exactly what this mean does. It's sort of the center of mass. And so what we do, and why not just take the absolute value? Well, mathematically, it's more complicated than that. So without getting into that detail here, we'll just square it. That will eliminate any negative signs. And then we average the squared deviations to get what we call the variance. So when you average the deviations, which here are your squared deviations, that's what we call the expected value. That's the average of those. And if you looked at it as an equation, it would be okay, average together all the x minus expected value of x squareds. And so you need to sum them up and then from the first all the way up to the nth, and then take their average. Now, if we take the square root of the variance, we get an actual practical measure that's called the standard deviation. So this is if you think about what we did with the variance, we squared all of the values. So if you had units here, and let's just say x had units of feet. Well, if you took feet minus feet, well, you'd still get feet, but then if you took feet minus feet squared, you would end up with feet squared. And so talking about spread in terms of, well, here's how spread out my measurements of these boards are in square feet. Well, that doesn't really make sense, right? So to talk about it practically, then you would take at the end of the square root of that variance, and that would eliminate the squares, giving you units of feet. And so oftentimes we use this Greek symbol sigma, to describe the standard deviation. But oftentimes we use the variance. Mathematically, it's just if you want to interpret it, it makes more sense to talk about standard deviation, because then you could say, well, on average, the feet are spread from the mean by blank number of feet. So let's go ahead and take a look at a sample computation. Let's say that we have the ages of 4 children in a family. They're aged 6, 8, 10, and 12. And so first of all, we begin by calculating the expected value. So the expected value, in this case, each of these has a 0.25 weight or 1/4 weight. So we can just add them up and divide by 4 in this case. And that would give us a mean of 9. Okay, so that means that on average, the average child is 9 years old. And again, remember what that really means is that if you could somehow redistribute the ages so that they're all equal, they would each have to be equal to 9 years for them to be have a total number of years of, in this case, 36 total years of age. So compute the deviation. So this 6-year-old is 3 years below the average. 8 is 1 year below the average. 10 is 1 year above the average. 12 is 3 years above the average. Now you can see these sum to 0. Therefore, not a good metric because these will always sum to 0. Think about that mean as providing a center of mass. So you have a 6-year-old, you have an 8-year-old, a 10-year-old, and a 12-year-old. They perfectly balance this scale. Expected value of x is 9, and so that's how the mean is calculated to provide this balance, and so they're going to sum to 0. And now we need to square them. So -3 squared, -1 squared, 1 squared, 3 squared. Add these up, you get 20. So this is not the variance quite yet, because we haven't averaged this out yet. This is just the sum of the square deviations. And so to actually get the variance of x, what we would need to do is to then divide this 20 by the number of observations, and we would get a variance of 5. Okay, now the variance by itself, as we've described, is not an entirely useful measure. It doesn't describe how spread out the data is, but this, remember, if x was in years, then squaring years minus years would give you years squared. So although mathematically we tend to use the variance instead of the standard deviation of the ages would be the square root of that, and the square root of 5 comes out to about 2.2, and that would now be in years. Okay, so this is the square root of the variance of x. And so now we could say that on average, and we don't mean a true average, right? Because we squared and then square rooted, and we did some funny stuff. So it's not quite, we didn't just take the average of the deviations, but we can kind of say on average, ages vary by about 2.2 years about the mean. So all we're saying that the average amount of, the average amount of spread from the mean is about 2 years. So it's a little more, right? Because you have this 6-year-old, which is 3 years away, and this 12-year-old, which is 3 years away, but then you have these two 8 and 10-year-olds that are only 1 year from the mean. So on average, it's about 2.2 years. So again, typically we just use the variance, but I want you to have a sense of what these numbers actually mean. Now, the variance is a special case of what we call the covariance. And as you can see in the word covariance, it's how two things vary together, or how two variables covary. Sometimes those two variables can be the same or different. Okay, so if they are the same, then you're talking variance. And if they're different, then you get covariance. So the only difference between variance and covariance is that covariance can be between two different variables. Variance is with respect to one variable. So for two different variables, rather than to take x minus the expected value of x quantity squared, you multiply x minus the expected value of x times y minus the expected value of y. You'll see how this actually is a very useful measure. It does indicate the extent to which two variables covary, but I just wanted to point out that statement that if the two variables are the same, you'd still use the same formula. It would be the expected value, but it would be x minus the expected value of x. That'd be for the first variable, right? And then multiplied by, for the second variable, it would be, again, x, because it's the same variable twice, minus the expected value of x. And so notice that this is just the expected value of x minus the expected value of x squared. Okay, so that's the special case of covariance where the variable is the same. Now, let's actually, usually we were interested in covariances between two different variables, but variance itself is a useful measure. Let's take a look at some data where, again, we have the ages of these 4 children, and maybe y is the time that they spend outside in hours. Okay, so clearly, the 12-year-old spending more time outside than the 6-year-old. And so we'd start off by, first of all, getting our expected values. Well, the expected value of x, we already know it's the same data as before, so it's 9. And now we would need to compute the expected value of y, which you could get the average of those, and that would give you an average age of 10. So again, we get the same x minus expected value of x, it's the same data, y minus the expected value of y. 8 hours outside is 2 below the mean of 10 hours outside, 9 is 1 below, and so on. Again, notice that these sum to 0. And so now you're going to multiply them together. Now, one thing that I want you to pay attention to here is that this data, x and y, covary quite a bit. You can actually see that if you were to kind of circle these points, you have a pretty tight ellipse. And the more elliptical, the more rubber bandy this looks, so to speak, most of the time you're going to have a much higher covariance, because we do actually see that they covary. As x goes up, y seems to go up as well. So if one goes up and the other goes up, then chances are, for the most part, when one is negative, so will the other. If one's below the mean, the other will be below the mean. If that's the case, then we're going to get a positive product. So again, these two are both below the mean, positive product. Not always, because sometimes, the mean may be lower for, like, the mean is in between for both data sets. It's in between these two values, right? The means are actually right there. Well, one of them is exactly 10. So as you sum these together, 15, you get 16 here. To get the variance, or the covariance between x and y, we would take the sum of the squared residuals, divide by the number of values, or not the squared residuals, but the sum of the product of residuals, and so you get a covariance of 4. Okay, so what that number doesn't really mean anything to us. It just means that that's a metric that describes how much these values covary. As a contrast, let's say that I change those values up, and now notice that as age goes up, the number of hours outside doesn't. Maybe it's hot summer in Arizona, and you can see that there's really not much variation in the data. It's just sort of a cluster. And so once again, if we repeat this, expected value of x is the same ages, and the expected value of y is now 1. So 2 minus 1 is 1, 0 minus 1 is negative 1, 2 minus 1. So again, notice these sum to 0 in both cases. Look at the products now. In some cases, they're negative, and in some cases, they're positive. That's because there really isn't much of a covariation. This one was 3 below the mean, but this one was 1 above the mean, so the product gives us a negative 3. These were both below the mean by 1, so we get a positive 1. And remember, we're summing these together, so now it's possible that we add positives and negatives. And here we get positive times a positive. Here we get a positive times a negative. So negatives and positives are going to counterbalance each other. Here we get a total of 4. And so in this case, the covariance between x and y is going to be 4 divided by 4, which is 1. And notice that that's a much lower covariance than it's 4, this one's 4 times higher than over here. So we should notice that the covariance, this is a negative 4. And the only significance of the negative, it just tends to tell us in which direction, whether there's a positive or negative relationship between the data. But again, notice that this is very close to 0. And the closer the covariance is to 0, the less they covary. So I'll just point that out. Covariances close to 0 show little mutual variation. Okay, so it is clear that variables with a clearer linear relationship will have a greater covariance. We'll just say by greater we mean absolute value, right? Because it could be positive or negative. And as it turns out, what's really handy is to be able to compute the covariance and the variance without having to do it in this fashion. This is just kind of a lot of work, and oftentimes it's much easier to just express the covariance in terms of the expected values. So the covariance formula can be expressed exclusively in terms of expected values, which makes computations less tedious. We could do some mathematics on the covariance formula, which we're not going to do here, but we would actually get the expected value between x times y minus the expected value of x times the expected value of y. These two things are already computed in the data. This thing is just this is a new quantity that we need to compute, but it turns out that it's pretty quick and easy to do. Again, if you do the covariance between a variable and itself, the only thing that changes is that you get the expected value of x times x, which is x squared, and then this would be the expected value of x times the expected value of x, which is not the same thing as the expected value of x squared. It's the expected value of x, quantity squared. Here you're squaring the expected value. Here you're squaring all of the x's. Different story. So, okay, let's compute the covariance here between x and y. So what we are going to need is we're going to need the expected value of x times y. So I'm going to need a column for x times y. I need to get those products, and then I'll just average those products together. It's basically what this amounts to. So here we'll get 48, here we'll get 72, 100, and 12 times 13 is 156. And now let's compute the average. So the average of x's we already know is 9. The average of the y's we determined was 10. And now what's the average of the x times the y's? Well, all we would do is just add these together and divide by 4. So 48 plus 72 plus 100 plus 156 divided by 4 gives us 94. So now, abiding by the formula, we have 94 minus 9 times 10, and that gives us a covariance of 4. And lo and behold, it is exactly the same covariance that we achieved up here in our initial age versus hours outside example. So much a simpler formula. Again, the only thing you do differently here, if you just wanted the covariance between x and itself, in other words, the variance between x or the covariance between x comma x, which is the same thing as the variance of x, you would just take the expected value of the x squareds. So 36 plus 64 plus 100 plus 144. I'm just squaring those x's, adding them together, divided by 4. You would get you would get 86, and then the expected value of x is 9. So you'd have minus 9 times 9, and that would give you 5, which once again checks out because when we computed the variance earlier, we did indeed get 5 as the variance. So just an easier, more convenient way to do this. Now, it's convention to write the expected value of x as mu. This is a Greek symbol. It's just done for convenience mainly because, to have to write down e of x, it's a little bit easier to write down mu. Let's suppose we have a collection of d states for random variable x. So let's just say that our random variable is actually, each instance is a single vector. And each vector may, for example, contain a child's age. So maybe we have that 6-year-old who plays for, we determined, 8 hours, and maybe they weigh, I don't know how much 6-year-olds weigh right off the top of my head, but we'll say 70 pounds. And so 8 hours outside, and then 70 pounds, and then maybe 42 inches tall, and so on. So basically, this would be what we call the first instance, or the first state, the second state, the third state, fourth state, and then down here we would eventually have the last state, x sub d. So we have d random variables. Now we compute this for each child, right? This would be for maybe child 1. If we do the same thing, we'd get another instance for child 2. And we'd get those, values that we obtained here as well. And so what we would want to do is we want to know, okay, what is the variance of all of the variables, so all of the states. So what's the variance of the ages? We already know that. What's the variance in the total number of hours they're outside? What's the variance in weight? What's the variance in height? Not only that, but we also want to know how these things covary. So I want to know how years and hours of play covary. We've already computed that. We found the covariance to be 4. But I also want the covariance between age and weight, age and height, time outside and weight, time outside. I want all the covariances, right? So what I'm going to do is I'm going to build a variance covariance matrix. This vector lives in Rd. It has d components, meaning it is a d by 1 vector. Each of these is a d by 1. And so what I'm going to end up with when I compute this variance covariance matrix, where the standard here, by the way, don't let this confuse you. This is the matrix is typically named capital sigma, not to be confused with summation. This is just the name of the matrix. Okay, it's going to be a d by d matrix. This is a d by d matrix. We can express that as the variance of that vector, which is the covariance between the vector and itself. Notice it's not the covariance between one state and itself exclusively. It's the covariance between one vector and the other vector. And so for the multivariate realm, notice this formula looks very, very similar to just for a single state, like we had just age or age and hours of play outside. But basically this matrix would look like this. In each entry, it would have the covariance between, if you map it out like this, you have x1, x2, all the way down to xd. and then you look at x1, x2, all the way over to xd along the columns, then each of these entries, like this one, will be the covariance between x1 and itself. So this right here is just the variance of x1. So the variance of the ages, which we already know is equal to 5. And then here you would have the variance or the covariance between the first variable and the second variable, and that would go there. So that would be the covariance between age and hours of play outside, and we already know, we computed this value to be positive 4. Now when you go down, now it's x2 comma x1, so it's always row and column variable, and notice that these are actually the same. Covariance between x1 and x2 is going to be the same thing as the covariance between x2 and x1. So these two values are the same, and so what it makes sense to me to do is it makes sense to think about this and this as the same. Okay? Along the diagonals here, notice that this is a variance between x2 and itself. This is a variance, so the diagonals are going to contain the variances, and then the off diagonals are going to contain the covariances. So again, notice that as you go across, this is all going to be between x1 and all the other variables, all the way up to xd. And then this column will be, the second component here will be x1, and then the first component will be the row that you're in. So notice that this is the covariance between xd and x1, which is the same thing as between x1 and xd. Furthermore, you can see here the covariance between x2 and xd is the same as the covariance between xd and x2. And so what we really want to point out here is that this is a symmetric matrix. It's a perfectly symmetric matrix. Meaning that the transpose of the matrix is equal to the matrix itself. Okay, that's a helpful property feature to have. So you might say, well, it's kind of redundant, isn't it? It's like, yeah, it is redundant. You don't need to go below the diagonal and above the diagonal. You really just need to focus on the diagonals and then either the entries above the diagonal or the entries below. All right, so it is possible that you have two different random variables, x and y, x having d states, so x1, x2, all the way down to xd, and then y having e states, y1, y2, all the way down to ye. And so, but the thing is, you have to have the same number of each of the vectors. And these there aren't going to be any variances here. They're all going to be covariances because x1 and y1 are different variables. So what you end up with is a d by e matrix. That'll look very similar. Something we'll return to later. I just wanted to point out that the two random variables do not have to be the same random variable. All right, almost there. So the question is, like with the covariances, how do we know how big a covariance actually is? How good is that fit based on the covariance? Well, when we've done regression in the past, like say you take a data set and you fit a line to it, you'd often look at the correlation coefficient, which a lot of times would be called R, not R squared. This is a value that's basically been standardized. It's a standardized covariance. And what it does is it forces R to be between -1 and 1 inclusive. So the beauty of this is that it doesn't matter what kind of data set you're looking at, the goodness of fits across two data sets can be compared because they're always going to be bound between -1 and 1. Think of these as proportions. So -1 is negative 100% and +1 is positive 100%, indicating a perfect fit. So the closer you are to 1 or -1, the better. So I'll just put this on a number line. 0 would be no correlation. They're not at all correlated. -1 and +1 would be a perfect negative correlation and a perfect positive correlation. What do we mean by that? Well, it's going to be a negative relationship if as one value increases, the other tends to decrease, versus a positive one is a perfect positive relationship. As one variable increases, so does the other. So this would have a positive correlation because as x goes up, so does y. And the way you do this is to get the correlation coefficient, you take the covariance and divide it by the square root of the products of the variances.